Order of a differential equation. Welcome, everyone. Today, we are beginning a new topic in calculus, the order of a differential equation. Now, before we dive into the complex calculations, we need to understand how to categorize these equations. In the study of different equations, the very first step towards solving or classifying an equation is identifying its order. You can think of this as identifying the level of the equation. Why is this important? Well, understanding the order allows us to determine the complexity of the equation, and, crucially, it tells us the number of arbitrary constants that will appear in its general solution. In the upcoming slides, we will learn exactly how to spot this order and how to distinguish it from other parts of the equation, such as the power or degree. Let's get started. 1. Understanding the concept. Now that we've introduced the topic, let's dive into the core concept. To understand what we are looking for, we first need to be clear on what a differential equation actually is. Essentially, a differential equation involves derivatives of a dependent variable, which we usually call y, with respect to an independent variable, which we typically call x. Think back to your basic calculus. A derivative simply represents a rate of change. Now, the key to our topic today is that we can differentiate a function multiple times. When we do this, we create what we call higher-order derivatives. For instance, the first derivative, written as di dx, is known as the first-order derivative. If we differentiate again, we get the second derivative, written as d squared y dx squared, which is the second-order derivative. We can keep going indefinitely. The nth derivative, written as d to the nth power of y, dx to the nth power, is simply called the nth order derivative. This brings us to our formal definition. The order of a differential equation is defined as the order of the highest derivative of the dependent variable present in the equation. If you find that a bit wordy, don't worry. In much simpler terms, to find the order, you simply look through the equation and identify the derivative that has been performed the most number of times. In our next slide, I will show you a step-by-step guide on how to apply this to any equation you encounter. 2 step-by-step guide to identifying the order. Now that we have established the definition of order in the previous slide, let's move into the practical application. I want to give you a clear, systematic approach so you can approach any equation with confidence. To determine the order of any given differential equation, you simply need to follow these 3 steps. Step 1, your first task is to scan the entire equation. Don't get distracted by the $x or $y terms or any constants. Instead, look specifically for all the derivatives present. You might see them written in Leibniz notation, like di dx, or as second derivatives, like d squared y over dx squared, or even in prime notation, such as y prime, y double prime, and so on. Just list them all out. Step 2, once you have identified the derivatives, you need to determine the order of each individual derivative you found. This is straightforward. If you see di dx or y prime, that is a first-order derivative. If you see d squared y over dx squared or y double prime, that is a second-order derivative. And if you encounter d cubed y over dx cubed or y triple prime, that represents a third-order derivative. Step 3, finally, look at your list and identify which of these derivatives is the highest. The number associated with this highest derivative is the official order of the entire differential equation. As we will see in the next slide, applying this simple 3-step process will help you avoid common pitfalls and correctly identify the order in even the most complex-looking equations. 3 illustrative examples. Now that we have covered the definition and the step-by-step process, let's put that theory into practice with some illustrative examples. First, let's look at example 1, which is a basic identification task. Consider the equation, di by dx plus 5x equals e to the power of x. To break this down, we first scan the equation to identify any derivatives. In this case, the only derivative present is di by dx. Next, we determine its order, and since this is a single differentiation, it is a first-order derivative. Therefore, our conclusion is that, because the highest derivative present is the first derivative, the order of this equation is 1. Moving on to example 2, this one is a bit more complex, because it tests your ability to distinguish between order and power. Look at this equation. The second derivative of y with respect to x plus 3 times the first derivative of y with respect to x, all raised to the power of 4 plus y equals 0. Let's break it down. First, we identify the derivatives present. We have the second derivative of y with respect to x and the first derivative of y with respect to x. Next, we determine their individual orders. The first term is a second-order derivative, and the second term is a first-order derivative. Now, we identify which one is the highest. The highest derivative is the second-order one. So, our conclusion is that the order is 2. I want to highlight a very important note here. Notice that the power of 4 on that first derivative does not change the order. It only affects what we call the degree of the equation. Finally, let's look at example 3 to see how this applies to a real-world scenario in physics. The motion of a simple harmonic oscillator, such as a mass bouncing on a spring, is described by the equation m times the second derivative of x with respect to t plus k times x equals 0. In this context, m represents mass, k is the spring constant, and x represents displacement over time t. When we break this down, we identify the derivative present, which is the second derivative of x with respect to t. This actually represents acceleration. We then determine its order, which is a second-order derivative. Consequently, we can conclude that this is a second-order differential equation. As we move to the next slide, keep a close eye on those powers, as they are a common pitfall for many students. 4 common mistakes to avoid. Now that we have seen how to identify the order through various examples, I want to pause and discuss some common pitfalls. Even students who understand the concept well can sometimes fall into these 2 specific traps, so please pay close attention here. Our first mistake to avoid is confusing the order with the power, which is also known as the degree. It is very common for beginners to see a large exponent on a derivative and mistakenly think the order is higher than it actually is. For instance, let's look at the term di dx, all raised to the power of 3. In this case, the order is actually just 1 because we are only looking at the first derivative. The number 3 is simply the algebraic power, or how many times that derivative is multiplied by itself. When you are scanning an equation, I want you to always focus on the derivative level. That is, how many times the variable has been differentiated, rather than the algebraic power. The second mistake involves misinterpreting the notation itself. This can be quite tricky because the notation looks very similar to squaring a term. For example, you might see the notation d squared y over dx squared. It is vital to remember that this notation represents the second derivative, which means the order is 2. On the other hand, if you see the notation di dx, all enclosed in parentheses and raised to the power of 2, that is actually the first derivative squared, meaning the order is only 1. As we move into our final summary slide, keep these distinctions in mind, as they are the key to accurately classifying any differential equation you encounter. 5 key takeaways. All right, we have reached the end of our lesson. To wrap everything up, let's review the key takeaways from today's session to ensure you have a solid foundation before we move on to more complex topics like the degree of an equation. First and foremost, remember that the order is determined solely by the highest derivative present in the equation. You aren't looking at the whole equation as a whole, but specifically searching for that one derivative that has been differentiated the most number of times. Second, keep in mind that the order is always a positive integer. You will encounter first-order, second-order, or even third-order equations, but you will never see a fractional or negative order in this context. Third, this is a crucial point where many students stumble. The order is completely independent of the powers to which the derivatives are raised. As we saw in our second example earlier, even if a derivative is raised to the fourth power, it doesn't change the order. It only changes the degree. Finally, when you are scanning an equation, your best strategy is to ignore the coefficients and the exponents. Don't let the numbers multiplying the terms or the powers distracting you. Instead, focus your attention strictly on the number of times the dependent variable has been differentiated. If you can master this distinction, you'll be well on your way to classifying any differential equation you encounter. Great job today!